So long before the advent of quantum mechanics, with its concept of discrete states for all physical systems, the phase space and the statistical mechanics predated quantum mechanics, possibly in the 19th century. Boltzmann's H theorem, the Boltzmann relation linking the macroscopic world to events at the microscopic level. The Maxwell-Boltzmann statistics and Gibbs' pioneering work on ensemble theory all were developed within the classical framework. So, in terms of classical phase space, there is 6n variables, namely qi and pi, the generalized momenta and the generalized coordinates, with a Hamiltonian function h is a function of q, p and t that we all know, and subsequently we may know a few constants of motion in terms of regarding the various statistical ensembles, the energy E, the number of particles N, volume V, beta or 1 upon kT, or temperature, such as the different variables for three statistical ensembles. So the most fundamental way to understand the foundations of the statistical mechanics by using the quantum mechanics, and in a finite system there are countable number of states with various properties such as the energy Ei, right? So in each energy interval we can define the density of states that we already discussed in the earlier classes, where the GEDE is proportional to exponential of S, which is the entropy of the system, over Kb times dE. So we have to discuss the environment of the system, and if my system is isolated, there is no contact outside of the world, so this is appropriate to describe a cluster in a vacuum. Or we have a system which is in contact with the heat bath, and replace the surrounding system with the heat bath. All the heat bath does is occasionally shuffle the system by exchanging energy, particles or momentum. In that case, the only distribution consistent with the heat bath is a canonical distribution, where the probability P dq dp is equals to e to the power minus beta h is a function of qp over z, where z is the partition function of the system. So we are discussing the ensemble theory, and we have been talking our way around a part of statistical mechanics called the ensemble theory. So this is the theory of how to use statistical mechanics to define averages in various situations. The sets of configurations or of quantum states used in the average is called an ensemble, and hence the whole subject is called ensemble theory. There are many different ways to define averages. However, there are three which are most commonly used. The canonical ensemble is the one defined in this lecture, having the classical probability distribution, which is proportional to exponential of minus beta h is a function of q and p. And in this ensemble we hold the particle number n fixed and integrate over all energies. It is evident that the microcanonical ensemble is fundamental and refers to the simple situation in which the constituent system are isolated and not influenced in any way by external disturbances. One would therefore think it proper to use such ensembles in the development of the basic theory. However, as pointed out, microcanonical ensembles are best suited for isolated systems, and we seldom deal with a completely isolated system. There is always some energy exchange with surroundings. It would be more realistic, therefore, to use an ensemble in which statistical equilibrium is attained not by isolation but by free interaction. Canonical ensembles have been found to be more appropriate for the description of such systems. Beside canonical approach gives results which apply even when components interact strongly, right? So this is the very basic regarding the constants of the system, where energy, volume and number of particles are constants in case of microcanonical. In case of canonical, the T, V and N is a thermodynamic variables. T, temperature, pressure and number of particles, is canonical for constant pressure, and TV mu, where mu is the new quantity introduced for in case of grand canonical ensemble, where we can vary the number of particles. So as I already discussed, that in case of microcanonical ensemble, we have to deal with the most probable distribution, and the procedures of counting the number of microstates omega and calculating the thermodynamic properties of the system therefrom are, as we have seen, cumbersome, to put it mildly. So a much simpler alternative is to find the most probable distribution. That we have already come across in the microcanonical, elucidating the microcanonical ensemble. So the microcanonical ensemble, though the most fundamental, is generally the least convenient to use because of the difficulties involved in evaluating the number of microstates accessible to a system or the volume of phase space available to it. The canonical ensemble invented by Gibbs proved to be much more tractable to mathematical manipulations. All the thermodynamic properties of the system emerging in a simple manner from a single function called the partition function or sum over states. A system placed in thermal contact with a heat reservoir is termed a canonical ensemble. It is specified by a fixed temperature, the temperature of the reservoir, instead of a fixed energy E. It is specified by a fixed temperature, and instead of E as in the case of isolated or microcanonical system. The nature of the heat reservoir is unimportant. Which is essential is that it should be large compared to our system so that its temperature remains constant during heat exchanges with the system. Any system in thermal contact with its environment, the larger system, is a canonical system. A canonical system therefore conforms to the actual physical conditions of most systems in the real world, whereas an isolated system is an idealization. Moreover, the temperature T is measurable by a thermometer and also controllable, being the temperature of the reservoir, whereas the energy E of a system is not directly measurable. A canonical system is specified by the number of particles N, the volume V, and the temperature T. So here we can write any function as a any function which is a parameter of n, p, and t. The grand canonical ensembles, also devised by Gibbs, is obtained from the canonical ensemble by relaxing the condition of a fixed number of particles n. A grand canonical system is one which, besides exchanging energy with a heat reservoir at temperature T, also exchanges particles with a particle reservoir with chemical potential mu. The grand canonical ensemble is the appropriate framework to discuss systems with variable number of particles, such as a photon gas, the Bose gas at low temperatures, coexisting phases of a substance in phase transition, etc. So let's derive the theory here for canonical ensemble. So as I have mentioned, suppose we desire to study the statistical properties of a thermodynamical system A. To this end, we envisage an assembly of a very large number of systems, n, identical in volume and molecular composition with A. Each system of the assembly is considered to be in thermal contact with a huge heat reservoir. A heat reservoir is a system whose heat capacity is so much higher than that of the subsystem in contact with it that heat flow from or to the heat reservoir does not change its temperature significantly. The assembly can be thought of as contained within a microcanonical ensemble. Each system of the assembly is in contact with other elements of the microcanonical ensemble but is otherwise isolated from the outside world. The walls of the containers of the system of the assembly, which separate it from microcanonical ensemble, are diathermic walls. I repeat, diathermic walls, which allow heat to flow through them but do not allow the exchange of mass. An assembly of this kind is called a canonical ensemble of a system of type A. The number of systems in a canonical ensemble is constant, but their energy is not fixed. Let us now find the probability that a canonical system under the yes so an assembly of this kind is called a canonical ensemble of systems of type A. The number of systems in a canonical ensemble is constant, but their energy is not fixed. So let us now find the probability that a canonical system under the condition of equilibrium is in a particular state with specific energy EA, right? So consider a canonical system A in a microcanonical ensemble A prime, where A is far smaller than A prime, as discussed in the figure. The walls of A are such that A and A prime are free to exchange energy. The microcanonical ensemble is isolated and this total energy E0 is constant. As discussed before, a large number of microscopic states correspond to the macroscopic state of the microcanonical ensemble with energy E0, and omega naught be the total number of microstates of the microcanonical ensemble with energy E0. By the postulate of equal a priori probability, all these microstates are equally probable. Therefore, the probability of each microstate is 1 upon omega naught. It is obvious that the different microstates of the microcanonical ensemble A prime will give rise to different microstates of the small subsystem A. Suppose a certain microstate of A prime gives rise to a microstate of A with energy EA, where EA is far smaller than E0. Hence, the energy of the remaining part of the complete system, that is E0 minus EA, this is one microstate of A with energy EA attained through the other microstates of A prime. Let the number of states of the microcanonical ensemble A prime through which the states of the small system corresponding to the energy EA are attained be omega A is a function of E0 minus EA. Therefore, the probability that the small system A is in state V A state with the energy EA is nothing but P alpha is equals to omega A E minus E naught minus EA divided by omega naught. So this is the equation 1. Using the relation alpha is equals to e to the power log A, we can express P alpha as e to the power ln omega A E naught minus E alpha divided by omega naught. So expanding this ln omega into a Taylor series, that is ln omega alpha E naught minus E alpha is equals to ln omega alpha E naught minus E alpha del ln omega alpha E naught divided by del E naught plus the higher order terms. So if we put del ln omega alpha E naught over del E naught as beta and neglecting the higher order terms, then it turns out to be ln omega alpha E0 minus E alpha is equals to ln omega alpha E0 minus beta E alpha. Hence, my P alpha becomes this, which is after a few calculation, this is constant times e to the power minus beta E alpha. So from the normalization condition, which is sum over P alpha is equals to constant times sum over e to the power minus beta EA, which is equals to 1, and therefore the constant becomes 1 upon summation e to the power minus beta E alpha, and P alpha becomes e to the power minus beta E alpha divided by summation of e to the power minus beta E alpha. This is the Gibbs canonical distribution. It gives the probability that the small system A be in a state with energy E alpha. There may be other microstates of A with the same energy E alpha. If this number is G alpha, then P alpha is substituted by G alpha times this canonical distribution type. So the denominator is usually represented by Z. That is, Z is equals to sum over alpha e to the power minus beta E alpha. Therefore, my P alpha becomes G alpha e to the power minus beta E alpha divided by Z. If E is a continuous variable, then Z becomes integration 0 to infinity e to the power minus beta E d E alpha. So we have yet to identify the parameter beta, which we will shortly do. Meanwhile, we shall discuss here an example which gives a clue towards the identification of beta. Consider a composite system A0 made up of two systems A and A prime in thermal contact and weakly interacting with each other. Let A be in state R with energy E2 and A prime is in state S with energy Es. The energy of the composite system A0 is therefore E0 is equals to Er plus Es. If the two systems are separately in internal equilibrium, the probabilities of finding them in respective states are given by PR is equals to e to the power minus beta ER divided by sum over R e to the power minus beta ER, and likewise PS is equals to e to the power minus beta ES, beta 1 ES divided by e to the power minus beta 1 ES. So these probabilities are statistically independent. Therefore, the probabilities PRS of the system A is in state R and A prime in state S simultaneously is given by the product of PR and PS, which is e to the power minus beta ER divided by sum over e to the power minus beta ER times e to the power minus beta ES divided by e to the power minus beta ES. Evidently, this does not correspond to a canonical distribution of the composite system and hence does not describe an equilibrium situation. Exchange of energy between the two systems therefore will continue until equilibrium is reached. Time taken by the systems to reach the state of equilibrium from its initial state of non-equilibrium is called the relaxation time. However, if beta is equals to beta 1, then this equation becomes Rs is equals to e to the power minus beta Er plus Es divided by sum over R and sum over S e to the power minus beta Er plus Es, which corresponds to the canonical distribution. Since the only criteria for thermodynamic equilibrium under these conditions is that the temperature of the two systems be equal, it is valid to assume beta as a function of temperature. I repeat, beta as a function of temperature. So let's move on to some different aspects. How do we calculate the mean value and the fluctuations? The mean of a function f alpha is given by f is equals to sum over alpha f alpha p alpha. This is a conventional technique. In the case of canonical distribution, this mean f is equals to sum over alpha f alpha times e to the power minus beta e alpha divided by sum over e to the power minus beta e alpha. Thus, the mean energy is given by sum over e alpha e to the power minus beta e alpha divided by sum over e to the power minus b alpha, which is sum over e alpha e to the power minus beta e alpha divided by z. Thus, the mean energy is equals to minus 1 upon z del beta, or this is minus del beta of ln z. The mean square energy, if we calculate in the same way, then E square average is equals to sum over E alpha square e to the power minus beta E alpha divided by e to the power minus sum over e to the power minus beta E alpha, which is 1 upon z del 2 z del beta 2. Therefore, the fluctuations of energy del E average is equals to average E minus E square, which is E square average minus E average square. Then if we put these values 1 upon z del 2 z del beta 2 minus 1 upon z square del z del beta whole square, then which is del 2 del beta 2 of ln z, which is minus del average divided by del beta. Using the relation beta is equal to 1 upon kt. And we get del E square average is equals to minus del E del beta, which is del E del t del beta, which is kt square del E del t, which is kt square times Cv. Therefore, the energy fluctuation in the canonical distribution is proportional to the specific heat. For example, for a perfect gas E is equals to 3 by 2 nkt. Therefore, delta E square average is equals to kt square times 3 by 2 nk, which is 3 by 2 nk square t square. Right? And the mean fractional fluctuation, which is del E square average divided by del E square to the power half, is equals to, if we put the values 3 n k square t square divided by 2 times 4 over 9 n square k square t square to the power half, which is 2 upon 3n to the power half. This is negligible if n is far greater than 1. So if capital N is equals to 1, this fractional fluctuation 2 by 3 to the power half is 0.82, showing that fluctuations are more important for microscopic system. If N is 10 to the power 18, say, which corresponds to a macroscopic system, fractional fluctuation is 0.82 times 10 to the power minus 9, which is negligible. It is therefore reasonable to assume that in thermal equilibrium, a macroscopic system has a precise energy value which is equal to the ensemble average value of energy. So for large systems for which n is at the order of Avogadro number 10 to the power 23, this n to the power minus half is a very small number. Hence the energy dispersion, which is proportional to 1 upon root n, is negligible, and we may take energy average is equals to energy, that is the mean energy is almost identical to the most probable energy or the thermodynamical internal energy. We see that if the system in thermal equilibrium with a heat bath is macroscopic and one the relative fluctuations in its energy are extremely small, if the system were isolated from the heat bath, its energy would not fluctuate at all. The distinction between these two cases for macroscopic systems is insignificant. It means that for all practical purposes, a macro system behaves in the same way whether we regard it as isolated NVE or whether we consider it as in contact with a heat reservoir NVT. Thus, NVE system such as a gas in a cylinder of constant volume V has a temperature T which is a unique function of NVE, even though its macrostate is specified in terms of its internal energy E. In other words, though T is not explicitly mentioned in the specification, it is implicitly present. The thermodynamic limit, the canonical ensemble is equivalent to the microcanonical ensemble, and one expects the canonical ensemble to reproduce the results obtained with the microcanonical ensemble. The great advantage of using the canonical approach is that the mathematics is much easier to handle. While the microcanonical system is macroscopic, the canonical system may be quite small provided that taken with the heat reservoir the composite system is large. For small systems, of course, n is a small number and the energy dispersion is by no means negligible. That the canonical formalism is applicable to a system, however small, which is in thermal contact with the heat reservoir, is shown more clearly by treating it as a member of an ensemble of replicas of the given system. So we quickly move on to the case of reduction of Gibbs distribution to Maxwell and Boltzmann distribution. Since we have claimed that Gibbs distribution is a general distribution, we should be able to derive Maxwell and Boltzmann distribution from it. So Maxwell distribution function gives basically the probability of finding a particular molecule in a certain range of velocities, say between u and u plus du. The system in this case is a single molecule in a heat reservoir. The gamma space is a 6-dimensional space, that is the M space. Since a molecule occupies in the phase space a volume h cube, the number of states of a molecule contained in a phase volume element d gamma is nothing but d gamma divided by h cube, which is phase space volume dx dy dz times dpx dpy dpz divided by h to the power 6, where h is the Planck's constant. According to Gibbs distribution, the probability of a system being a state with energy E alpha is e to the power minus beta E alpha divided by sum over e to the power minus beta E alpha times G alpha. Therefore, the probability of finding the system in phase volume element B gamma corresponding to the energy E alpha is dp alpha is equals to e to the power minus beta E alpha divided by sum over e to the power minus beta E alpha divided times b gamma over h cube, which is e to the power minus beta E alpha divided by sum over e to the power minus beta E alpha dx dy dz dx dpy dpz divided by h cube. So to find the probability that the molecule has energy E alpha, we have to integrate this equation with respect to all the elements of the phase volume corresponding to E alpha. Since the energy does not depend upon the coordinates, we can straight away integrate and write dp alpha is equals to v by h cube e to the power minus beta E alpha divided by sum over e to the power minus beta E alpha times dpx dpy dpz. By converting into spherical coordinates and integrating over all the angular coordinates, we have dp alpha is equals to 4 pi v by h cube to the power minus beta E alpha divided by sum over e to the power minus beta E alpha p square dt. Now this free energy E is equals to half mu square, and the momentum is nothing but mu. So if we substitute these two equations, my dp alpha becomes 4 pi b by h cube e to the power minus beta mu square by 2 sum over e to the power minus beta mu square by 2 m square u square m du. So 4 pi b m cube divided by h cube e to the power minus beta mu square by 2 sum over e to the power minus beta mu square by 2 u square du. If we use the normalization condition, which is integration 0 to infinity dp alpha is equals to 1, then it turns out by a simple calculation of the integration, which is the gamma function, it's gamma half, and if we put the value of gamma half, this is finally turns out to be 4 upon root pi beta m by root pi to the power 3 by 2. Hence, dp alpha is equals to 4 by root pi beta m by 2 to the power 3 by 2 to the power minus beta m square u square by 2 u square du. So this is Maxwell's distribution. Comparing this equation with the earlier one, we see that two relations differ only in the constants appearing in them and will be identical if my beta is equals to 2 alpha m is 2m by 2m kt, which is 1 upon kt. This relation can also be proved by using this beta is equal to 1 upon kt to calculate the mean kinetic energy as mu square by 2 average is equals to integration 0 to infinity half mu square times this distribution function. And if we calculate this in a simple manner, it turns out to be the average of half mu square is equals to 3 by 2 kt, which is 3 by 2 beta. So where beta is equals to 1 upon kt. Hence the Maxwell distribution is dPu is equals to 4 upon root pi m by 2 kt to the power 3 by 2 to the power minus m by 2 kt u square du. So next we move on to the concept of chemical equilibrium, where the new quantity mu is introduced, right? So as thermodynamics aims at studying phenomenologically the properties of material bodies characterized by macroscopic parameters, we know that the matter in the aggregate can exist in states which are stable and do not change in time. The mechanical properties characterizing these equilibrium states, however, change with temperature. And from the knowledge of thermodynamics, the reversible and irreversible process, we can formulate these all the conventional equations of thermodynamics by using the different ensemble theories. And if we interpret the physical interpretation of alpha, which is z is equals to e to the power minus alpha, which is e to the power mu by kt. Alpha is equals to nothing but minus mu by kt, which is minus beta mu. This comes from the theory starting from the first law of thermodynamics, du is equals to dq minus dw. And if we put the different values, particularly the Boltzmann equation, entropy is equals to ln omega, then this special relationships where alpha is related to the chemical potential by the relation of fugacity, which is z, and therefore z is equals to e to the power minus alpha, which is e to the power mu upon kt. So now we are deducing the chemical potential in the equilibrium state. Consider two systems A and A1 with particles N1 and N2 and chemical potentials mu1 and mu2 respectively. Suppose that the temperature and the pressure of the systems are the same and that they are in contact being separated by a permeable partition. So the free energy is given by F is equals to Q minus Ts, and therefore dF is equals to what? Du minus Tds minus Sd. So my du becomes Tds minus Pdv plus sum over mu I dni, and therefore dF is equals to minus Sdt minus Pdv plus sum over mu I dni. If T and V are maintained constant, then dF is equals to sum over mu I dni, and therefore in the example under consideration our total dF is equals to mu1 dn1 plus mu2 dn2, mu1 d1 plus mu2 dn2. dn1 and dn2 are the changes in the number of particles on the two sides of the partition, and if the composite system is closed, n1 plus n2 is constant. Therefore dn1 plus dn2 is equals to 0, that is dn1 is equals to minus dn2. Therefore my df becomes mu1 minus mu2 times dn1. If the composite system is in equilibrium state, then del f del n1 is equals to del f del n2 is equals to 0. And therefore minus mu1 minus mu2 is equals to 0, which is mu1 is equals to mu2. We therefore conclude that if a system is to be in equilibrium state, temperature, pressure and chemical potential must be constant throughout the system. So let's go to the calculation of entropy. Thermodynamic functions in terms of the grand partition function, where we can write the entropies in the form S is equals to minus K sum over Pni ln Pni. Now Pni is nothing but e to the power minus beta Q Ni minus n mu divided by Z. Therefore S is equals to minus K sum over Pni log e to the power minus beta Uni minus n mu divided by Z, minus K sum over Pni beta mu Uni plus beta n mu minus ln Z. After two lines of calculation, this turns out to be okay K beta U average internal energy minus K beta n average mu plus K ln Z. So the other relations defining thermodynamics potential take the following forms in respect of the grand canonical ensemble. And the internal energy U is Ts minus Pv plus mu sum over Ni, and du is equals to Tds minus Pdv plus mu sum over Ni. The Helmholtz free energy F is equals to U minus Ts, which is mu times n average minus Pv. The enthalpy H is equals to U plus Pv, which is mu times n average plus Ts, and the Gibbs energy G is equals to U minus Ts plus Pv, which is mu energy average. The above relations have been obtained for a PVT system. They would be generalized by introducing generalized force Y and a generalized displacement X in place of V, and then it would be replaced by du is equals to Tds plus y dx plus sum over I mu dni, right? So one can calculate in term for ideal gas where the potential energy of interaction is negligible, where U is equals to 0, and this is a good approximation particularly in case of rarefied gases. And the total energy of an ideal gas consisting of n molecules of each m mass m is E is equals to sum over I is equals to 1 to n p1 square by 2 times m. one can calculate PV equals to energy relation by calculating the partition function. The energy average is equals to 3 by 2 nkt. The specific heat is equals to 3 by 2 nk. The free energy is equals to minus nkt ln by mkt divided by h square to the power 3 by 2 v, and the entropy is equals to nk ln v plus 3 by 2 ln p plus sigma, where sigma is equals to 3 by 2 ln 2 pi mk by n square plus 1. So the thermodynamic functions given here are derived on the assumptions that the molecule of the gas are distinguishable. However, it is easy to show that this assumption leads to results in contradiction with experience. We will show that how the computation of entropy of a classical ideal gas leads to a paradoxical result for the case when two equal volumes of the same gas are mixed together. So this is known as the Gibbs paradox. Suppose there are two different ideal gases, one composed of N1 molecules and another of N2 molecules. Let V1 and V2 be the volumes that two gases occupy. Suppose further that these gases are separated by a membrane and they are at the same temperature and pressure. If the membrane is now removed, the two gases will mix, but there will be no change in the energies of the two systems so long as the temperature remains the same. Let us now calculate the resulting change in entropy using the earlier equations. The entropies of the two systems, therefore, before mixing are S1 is equals to N1K ln V1 plus 3 by 2 N1K 1 plus ln 2 pi M1 KT divided by H square, and S2 is equals to N2K ln V2 plus 3 by 2 N2K 1 plus ln 2 pi M2 KT divided by H square. So this is the situation where after the membrane is removed, the entropy of the composite system, therefore before mixing, is given by sum over Si equals to S1 plus S2. After the partition is removed, the diffusion is completed, the gases are mixed and occupy a volume, total volume V1 plus V2. The temperature and the pressure of the mixture remains the same, this is T1 and P. The change in the entropy for each component in the process of mutual diffusion is obtained from the other equations, where delta S1 is equals to N1K ln V1 plus V2 minus N1K ln V1, which is N1K ln V1 plus V2 divided by V1. Likewise, delta S2 is equals to N2K ln V1 plus V2 divided by V2. Hence, the total change in the entropy of the system is delta S is equals to delta S1 plus delta S2, which is K times N1K ln V1 plus V2 divided by V1 plus N2 ln V1 plus V2 divided by V2, which is positive and is known as the entropy of mixing. This result is experimentally correct. When the membrane is removed, the molecules of one gas diffuse into the region which was previously occupied by the other gas alone. The diffusion process is irreversible, for by reinserting the membrane into the system, one would obtain two samples of the mixture and not the two gases that were originally present on mixing. Therefore, the entropy of the combined system must increase. However, a paradoxical situation arises when we consider the mixing of two samples of the same gas. Suppose two equal volumes of the same gas are at the same temperature and pressure and contain the same number of molecules, right? This is N, this is also N. So after mixing, it becomes 2B and 2N, but the temperature and pressure remains same, T1 and T. So since in this case V1 is equals to B is equals to B and N1 is equals to N2 is equals to N, my delta S becomes 2K N ln 2. This indicates that the removal of a partition between the equal volumes of the same gas causes an increase in the total entropy, which means that the entropy is not an extensive quantity. Further, one can imagine that the present state of the gas is arrived at by removing a number of membranes that initially divided the container into any number of compartments. Since there will be increase in entropy with every membrane removed, the entropy could be longer than any number. This result is delta is equals to 2k ln 2 unacceptable because the mixing of the two samples considered above is a reversible process. We can insert the membrane back to its position in the system and obtain a situation which is in no way different from the one we had before mixing. The total entropy of the combined system therefore should not change. This paradox is known as Gibbs paradox since it was discussed first by Gibbs. Paradox can be resolved only within the framework of the quantum mechanics. The molecules of an ideal gas are indistinguishable. I repeat, the molecules of an ideal gas are indistinguishable. Therefore, a permutation of the n particles in a given state cannot alter the state of the gas. Thus, if we consider two configurations which differ from one another merely in the interchange of two molecules in different energy states, in view of the indistinguishability of the molecules, the configuration are not distinct. While according to our classical mode of counting, we would regard them as two distinct configurations. In the treatment of the classical ideal gas given in the preceding section, we have therefore overcounted the states by assuming the molecules to be distinguishable, and that permutation of n molecules would lead to n factorial different states. In correct counting, there would be 1 upon n factorial fewer states. The correct translational partition function for the ideal gas, therefore, z is equals to e to the power n divided by h to the power 3n, but this 1 upon n factorial is overestimated. So